Hi everyone, I am Harsh and I'm going to give a presentation on the LTI systems. To start with, let's first understand what is a system. A system is basically a function that takes in an input signal and gives an output signal depending upon the type of the system. Broadly, we have two types of system, which are continuous systems and discrete systems. In continuous systems, the input and output both are continuous signals, whereas in discrete systems, the input and output both are discrete signals. Let's see the other classification of systems, which are static and dynamic system, causal and non-causal system, time invariant and time variant system, linear and non-linear system, invertible and non-invertible system, and stable and non-stable system. Since in this presentation we are going to discuss about LTI systems, LTI which stands for linear time invariant, we need to understand what are linear systems and what are time invariant systems. So now let's talk about time invariant and time variant systems. In order to understand this, we see two cases. In the first case, is an input signal xt is fed to the system, which gives an output as yt, and then it is delayed by certain time, say t naught, which should not be equal to 0. The final output is yt minus t naught. In the second case, we delay the input signal by certain time t naught. So the input signal is xt minus t naught. Now this is fed into the system, and let's say the final output is y dash t. So there are two possibilities. Either y dash t can be equal to yt minus t naught, or it cannot be equal to yt minus t naught. If it is equal, then we say that the system is time invariant. Otherwise, the system is time variant. Let's see some of the examples to make it more clear. In the first example, we have the system relationship as yt equal to x2t. So xt when fed to the system gives output as x2t, and in the first case we delay yt by certain time t naught, and the final output is x2t minus 2t naught. In the second case, the input signal xt is delayed by certain time t naught. So we have xt minus t naught, which is fed to the system, and the final output is x2t minus t naught. One thing we must note here that the constant 2 is only being multiplied to the variable time t and not the constant t naught. Since output of both the cases are not equal, we say that this is a time variant system. And in the second case, the system relationship is yt equal to 2 plus xt. Xt when fed to the system gives 2 plus xt as output, and now this output is delayed by time t naught to give us the final output as 2 plus xt minus t naught. In the second case, we delay the input signal uh, to get xt minus t naught. Now this is fed to the system, and the final output is 2 plus xt minus t naught. Since the output of both the cases are equal, we say that this is a time invariant system. Now let's see what a linear and nonlinear system. To understand this, we need to understand two of its basic concepts, which are law of additivity and law of homogeneity. Let's see what law of additivity is. In law of additivity, we have two different input signals, x1t and x2t. And in the first case, both the input signals are separately fed into the system. Let's say the output of both the input signals are y1t and y2t. Now these output signals are added to get the final output as y1t plus y2t. In the second case, we first add the input signals. On addition, we get x1t plus x2t. Now this added input signal is fed to the system, and let's say the output we are getting is y dash t. Here there are two possibilities. Either y dash t is equal to the output of the first case, or it is not equal. If both are equal, we say law of additivity is followed, otherwise it is not being followed. Now let's see what law of homogeneity is. In law of homogeneity, we have an input signal xt. It is fed to the system, which gives output as yt. Now this output signal is multiplied by certain constant k to get the final output as kyt. And in the second case, we first multiply the input signal by the same constant k, and the kxt input signal is fed to the system, and let's say the output we are getting is y dash t. If y dash t is equal to kyt, then we say that law of homogeneity is being followed, otherwise it is not being followed. Um, Now let's see one example to make it more clear. One thing we need to understand here is that in order for a system to be linear, it must follow both the law of additivity and law of homogeneity. If any one of the rule is being not followed, then we say that system is non-linear. So the example here is yt equal to x sine t. So two different input signals here are x1t and x2t, and when they were fed to the system, they give output as y x1 sine t and x2 sine t. Now these are added to get the final output as x1 sine t plus x2 sine t. And in the second case, we first add the input signals. The added input signal is x1t plus x2t, and now this is fed to the system, and we see that the final output we get is same as the output in the previous case. So we say here that law of additivity is being followed, and similarly we can see that law of homogeneity is being followed. So we can say that this system relationship is linear in nature. Now let's summarize what are the prerequisites for a system to be LTI. It must follow the rules of linearity of system and also the rules of for time invariant system. So some rules of linearity of system are it must be independent of time scaling, it must be independent of coefficient use and system relationship, etc. And some rules for time invariant system are there should be no time scaling and coefficient of system relationship should be constant, etc. So these are some of the rules that need to be followed. Um, so now we need to understand one more important concept, that is impulse response. So impulse response is necessary to understand in order to realize the other properties of LTI systems. And impulse response is simply the output response that an LTI system gives when input signal is impulse. We see that most of the examples we see are in time domain. Time domain meaning to say that the variable in the system relationship is time, and it is difficult to calculate impulse response in time domain. So we need to shift to the frequency domain in order to calculate impulse response. To shift into frequency domain, we have a Laplace transform. Let's say we have a signal which is ft and its Laplace transform is Fs. The calculation of Fs can be done by the formula which is integral from minus infinity to infinity ft e power minus st dt. So this is the formula used for calculating Laplace transform of a signal ft. So for the given example, which is yt equal to xt minus 1 plus xt plus 1, when we calculate Laplace transform, we get ys equal to xs e power minus s plus xs e power s. Now, let's see what is transfer function. Transfer function is the ratio of Laplace transform of the output signal to the Laplace transform of input signal. So when we calculate the transfer function of this system relationship, we get hs as e power s plus e power minus s. Now we need to understand one more concept, that the transfer function is the Laplace transform of impulse response. So in order to calculate impulse response from the transfer function, we need to calculate inverse Laplace transform of the transfer function. So upon calculation of inverse Laplace transform of transfer function, we get impulse response ht as delta t minus 1 plus delta t plus 1. So the system, so for the given system relationship, this ht is the impulse response. So this is important as this helps to understand various properties of LTI system. Now there can be different types of LTI systems such as static LTI system or causal LTI system. Let's see what are static LTI system. So for a system to be static LTI system, it must be static as well as linear as well as time invariant. As we have seen what are linear and time invariant systems. Let's see what is a static system. So if the final output is only depending upon the present value of input, then we say the system is static. Otherwise, if it depends upon past or future values of input, then we say that the system is dynamic in nature. Let's understand by some of the examples. The first example is yt equal to xt plus 2. If we put t equal to 0, we get y0 equal to x2. We see that the output is dependent upon the future value of input. So we cannot say that this is a static system, and hence it is not a static LTI system. Similarly, in the second case, yt equal to x2t, here we have time scaling. So if we put t equal to 1, we get y1 equal to x2. And here also the present value of output is dependent upon the future value of input. So the system is also not static LTI. In the third example, we have yt equal to sine of xt. We do not need to see whether it is static or dynamic, since this system relationship is not linear in nature. And in the fourth example, we have yt equal to integral from minus infinity to t xw dw. Since we know that integration is summation of area under the curve, and for calculation of present value of output, we need to take into account the previous values of input. So we cannot say that this is static system, as past values are also coming into it. Hence, it is not a static LTI system. Let's now see some of the real life examples of LTI system. So any image processing is LTI system. For example, rotation takes 2D input image and gives 2D output image. Other example can be speech production, speech recognition, speech processing, enhancements, etc. And mechanical systems, communication systems, etc. also use LTI systems. So this was it. Thank you very much.